In this series of videos, we're going to look at applications of derivatives using Larson Calculus 7th edition. And specifically, we're going to find critical numbers, find the open intervals on which the function is increasing, decreasing. We're going to locate relative extrema, etc. That's what we're going to do, and I'll work on the odd problems in this section. So we start off with f of x equals number 11. F of x is equal to x squared minus 6x. First thing we're going to do is find the first derivative, 2x minus 6. We're going to set that equal to 0. Set that equal to 0, and we get, when 2x is equal to 6, or x is equal to 3. And the next thing we're going to do with that is make a number line. We're going to plot our critical numbers. In this case, it's only x equals 3. We're going to select some test values in each interval. So that would be 0 and 4. And again, we're testing the first derivative here. So we go back, plug in 0, we get negative. Plug in 4, we get a positive value. All right, and so what this tells us is that the first derivative is negative from negative infinity to positive 3, and it means that the function is decreasing there. And then the first derivative is positive from 3 to positive infinity, and so the function is increasing there, and we have a minimum, a relative minimum, at x equals 3. All right, so I'm just going to quickly jot that information down. Now, it's not just enough to have the sign chart there. You do have to summarize the information in it. And I'll go on to number 13 next. And so we have f of x is equal to negative 2x squared plus 4x plus 3. And we'll find the first derivative. That's negative 4x plus 4. And that's going to equal 0 when x is equal to 4, or x is equal to 1. Once again, we're going to make our sign chart. We're going to plot our critical numbers, which in this case is x equals 1. We're going to pick some test values in each interval, 0 and 2. F prime of x is what we're working with. And we're going to go back and plug into the first derivative. So plugging in 0, I get positive. Plugging in 2, I get negative. And so we know that the function is increasing from negative infinity to 1, decreasing from 1 to positive infinity. And so we have a relative maximum at x equals 1 there. So we say that f of x increases on negative infinity to 1. F of x decreases on 1 to infinity. And we have a relative maximum at x equals 1. If we're looking for the y coordinate, we would have to plug back into the original function. In this case, y would be negative 2 plus 4 is 2 plus 3 is 5, I believe. Again, when you're looking for the y coordinate of the relative max, you're not going to plug into the first derivative. You're going to plug back into the original function. In number 11, x equals 3 would have given us 9 minus 18, which would be negative 9. All right, we're going to go on to number 15. And so we have f of x is 2x cubed plus 3x squared minus 12x. The first derivative would be 6x squared plus 6x minus 12. And I'm going to factor out a 6. I get x squared plus x minus 2, and that will factor to be x plus 2 times x minus 1. And we know that is equal to 0 when x equals negative 2 or x is equal to positive 1. So once again, we're going to make our number line. We're going to plot our critical numbers, which are negative 2 and positive 1. We're going to find test values in each interval. So negative 3, 0, 2, and again we're testing f prime of x. I'm always going to use the factored form, so when I plug in negative 3, I get negative 3 plus 2, that's negative. Negative 3 minus 1, that's negative. So negative times negative is positive there. Plug in 0, I get positive times negative is negative. Plug in 2, I get positive, positive, and that is positive. So that tells me that this function is increasing, then decreasing, then increasing again. And we'll have a relative max at negative 2 and a relative min at x equals 1. So once again, we state that f of x increases on negative infinity to negative 2 or on 1 to infinity. And f of x decreases on the interval from negative 2 to 1. We have a relative max at x equals negative 2. If we wanted to find the y coordinate that goes with that, we would plug back into the original function. And we have a relative minimum at x equals 1. Again, to find the y coordinate, we'd plug back 1 into the original function, not into the derivative. So we could find the actual point on the graph at which the relative minimum occurs. So that's going to do it for this video. We'll go into some more examples in the next.